So this is my presentation on, I suppose, my PhD as a whole, but specifically the analysis of magnetic gear systems using Infolytica MagNet, which I'll talk about in a bit. A lot of these slides, the first half, I think most of you will find quite interesting. It's pretty similar to the talk I did for Renewable Power Generations Conference down in London. And then the second half will be much less interesting, but it's much more, I suppose, valuable in terms of work that's actually being done. So, so my general PhD started off looking at non-mechanical speed enhancement techniques. So this could have been like a range of things at the start. But after a technology review, I decided that the most promising technology was the magnetic gear system. So we decided to focus on that. And my PhD is part of the larger Supermarine project, which I will advertise. It's an e-drive. The whole goal is to develop an integrated electrical power takeoff system that will work across a wide variety of wave power devices. And then again, like focusing on like adaptive control and reliability. We have a lot of parts. So it's mostly between us and University of Newcastle, but we also have industrial partners out there in Columbia, Technalia, Carnegie, Turbo Power Systems, who we haven't heard from in a while, but I think they're still there, aren't they? Yeah. And then also also academic partners, Delft University, Universidad de Chile, and Universidad Nacional Autónoma de Mexico. So why magnetic gears? Why would we bother looking at all? So there's some issues that exist across all wave and tidal energy devices. Extremely high operation maintenance costs. These devices are operating in like a high scaling, so a lot of salt environment isn't conducive to good mechanical interactions. Often operate in quite remote areas and dealing with quite both high and highly variable forces. And of course, the fact that both wave and tidal is quite low frequency, it's not very conducive to generating useful electricity at the 50-60 hertz that is generally used. Just for the work for RPG, I looked at in the kind of current solutions are either the typical mechanical gear or a direct drive. But as we know from, I suppose, the closest comparable technology, wind. A mechanical gearbox is a leading cause of downtime in these devices. So this would be a cumulative, whereas they may not break down quite a lot. When they do break down, it's pretty much a whole system overhaul. And again, so that would be associated with the highest cost of repair. But then if we look at direct drive, not only are we dealing with a much physically bigger system due to the high pole number requirements, which will increase installation issues. Again, because you're talking about you're going to have to hire a ship and install this, and then you're bringing in weather windows, which are quite strict in terms of safety. But also, interestingly, I found a study that said that overall, the fully rated power electronics result in comparable downtimes in comparison to the mechanical gear. So it's not really a solution. And then a lot of the other systems tend to use intermediate power takeoff methods, such as hydraulics. But these have their own problems if they're not generally standardized, and they can often suffer from poor efficiency, and they have their own operation maintenance issues. So why we think that magnetic gear technology is the best solution, possibly, it's contactless torque transfer. So there aren't any physically mechanically meshing parts. So this effectively reduces, except for I suppose the bearings, which would exist anyway, it reduces the wear and tear in the system massively. Also, you have much less lubrication requirements, which is another factor in operation maintenance. And but you still have, you have the advantage of a direct drive, but without the massive size. So the machine sizing, it still reduces it. I mean, it still has the same effect as the traditional mechanical gear in terms of its speed, size, torque, relationships. And another kind of quite unique advantage of magnetic gears is, as I said, I suppose especially wave energy of highly variable forces, very positive potential advantage in magnetic gears is that when the system experiences a sudden step change in force, if this is too much torque for the system, the magnetic gear would just slip and then realign itself. So it has high reliability in this case, whereas a mechanical gear would just shatter itself. Also, the stages are hermetically sealed from each other, so whereas it's not technically proven yet, but I think it could be. You have additional options with regards to the sealings for marinization, because they can be physically sealed away from each other. So let's do this because I want to get on to the actual results. But so the magnetic gear technology has actually been around for over 100 years, but at the start it wasn't very good, because they pretty much relied on poor magnetic material, and they relied on direct traditional gear substitution. So you had like the rack and pinion, or you had just like the external spur gear. So a lot of magnetic material and poor utilization, resulting in poor torque. It was more of an academic endeavour as opposed to like properly developing industrial applications. We got some renewed interest in the 1980s with the development of neodymium iron boron. This is a very high quality magnetic material, but again, because they were still relying on poor design, it didn't get much traction in the industry. So as of in this century, we have three kind of leading magnetic gear design types. The harmonic gear, the magnetic planetary gear, and the concentric gear, which would be the main focus. All of these have extremely high torque densities. It's 100-200 kilonewtons per meters cubed. It's very comparable to traditional mechanical gears. So I suppose you can see the main problem with the planetary gear, where it does have some advantages, such as the three modes of torque speed relationship. It's not fully utilising all of the magnetic material in the system, so you have redundancy, and it's just increased cost. The harmonic gear is a fantastic idea. It's huge torque capabilities, but it relies on a deformable inner high-speed rotor, which is extremely difficult to build. I'm not entirely sure if they've actually built a working sizable prototype yet. And then we have the concentric gear, which is by far the simplest and the leading one to do. Is most done by tidal and Magnumatics done in Sheffield. So you have, I think, was the next thing to talk about it? Well, it's not about here. So you have a outer low-speed rotor with a high pole number, and then on the inner rotor you have low pole but high speed, and then in the air gap in between you have ferromagnetic poles, which effectively they modulate the magnetic field interaction between the rotors, which I'll talk about more later. But this actually creates a change. It sets up the torque speed relationship. So it's leading because it's the simplest to implement. You don't have the form membrane or the high bearing requirements of the other ones, but it's also highly adaptable, which could be hugely useful in marine energy. So we have an axial form, and you can also make a linear form. So the gear ratio is determined by two main modes of operation. So one of the rotors has to be stationary. So typically you would either hold the ferromagnetic pole rotor or the low-speed rotor stable. So this will do two things. If you allow the ferromagnetic pole rotor to rotate, the magnetic field rotates in the same direction, which you may want, and you can get a slightly higher gearing ratio, because the ferromagnetic pole pieces are determined by the number of pole pairs on the low-speed outer rotor and the number of pole pairs on the inner rotor. Any questions? I'll be happy to answer. Kind of flying through it. But I have some slides that kind of better demonstrate it a bit further on. So this was just the main part of the paper was just to show how ready this technology is to be integrated into marine energy devices. So I chose three quite varied devices. I think that's the Atlantis bladed tidal turbine. It's the Canadian buoy, and then you have the failed it's the oyster device. But I mean the principle works for any oscillating wave searching further. So this is an already developed model that they built and tested. So this would be for just a typical tidal turbine device. And as you can see, so it's directly built. So it's a massively compact system, and the magnetic gear is directly built with the generator on the inside. So the force or the torque is generated by the rotor, just goes straight into the low-speed rotor. You get that step speed change, and then the generator just sees the speed change. But as young he said, there's a lot of magnetic material in that space, so a lot of analysis will have to be done. So this was just for a heaving buoy model, and this was another group that proposed this. So you have a kind of a concatenated linear magnetic gear with a linear generator, and so the experience is just that step change again. Fairly complicated system. I mean, the bearing's going to be quite hard to build in this, but they saw a huge reduction in both size and cost, but that was for pure just material cost. And then I don't have any nice pictures for this, but so the Oyster originally used a hydraulic system, but my proposal for it would be to use either an axial or a concatenated, just simple one similar to the tidal turbine, and you can see it would easily kind of go in. But it was for this device and these torque requirements that my work now is taking me. So what I'm trying to do is design a magnetic gear that would fulfill the torque requirements for this device. So then this is kind of starting the direct industrial application. And can I help with this? Because a central point of my PhD is to develop the design tools in either analytic models or 3D modeling models that would help for kind of quick and easy initial design and testing of magnetic gears before you go to any further kind of prototype scale or anything. So this is what you would get if you designed it in Infolytica MagNet. So MagNet is compatible with Visual Basic. So I've written a script that will design you pretty much any, like as in any order of, or any variable of parameter that you would want in this. So that's pole size, magnet height, axial length, back iron length. So as in the whole thing is direct, and it takes it takes 2 seconds to actually compile, but then running times vary hugely depending on because I suppose unfortunately the main, not unfortunately, but as in the main elements you're interested in are what's happening in the air gap between your rotors. So even though you might have, you could have a 6 meter diameter air gap, but for anyone familiar with finite element analysis, you're going to need quite small elements in the actual air gap between them, which massively increases at runtime. So the majority of my analysis and tests were run in 2D, and I can talk a bit more about that later. So this kind of best shows, didn't come out at all, cool. So this kind of shows what the effect of adding the ferromagnetic poles into the air gap between the rotors. So this is looking at, thing there? Doesn't really matter. So this is looking at what the inner rotor would see if the inner rotor magnets were taken out. So this is just the magnetic field being created by the outer rotor. So initially you have, without the ferromagnetic poles, and just see so this gear was, I think there was 8 magnetic poles in the inner rotor, and there was 46 on the outer rotor. So we can see that it's just creating pretty much nonsense here. This was with, so as I said, the inner rotor magnets are considered air, but we're testing at the point they would be interacting with the magnetic field, and there are no ferromagnetic pole pieces. So but then when we put them in, we see a very clear peaking. So it's been very clearly separated into the 8 that would then align with the magnetic poles in the inner rotor. And this is where we see this, the start of so this alignment is where you're seeing your first bit of your speed change. And then the reverse of this is also true. So this is the opposite end. So this is the magnetic field created by the inner rotor and the outer rotor. First with no ferromagnetic poles, and then with ferromagnetic poles. So you can see the clear modulation there between the 8 peaks that would create an inner rotor to, I think it's like 46 there, which is working, which is great. So this kind of better shows the, this is actually showing our speed increase, and it actually shows the torque change as well. So this is all for the same magnetic gear. So what's happening is, see a little bit up and maybe way bigger. So for this test, all components were there, but I rotated each rotor separately by holding the other stationary, just to see the overall torque change of the system. So what we would expect knowing from the gearing ratio is that so changing your ferromatic pole rotor will result in the highest or the fastest torque change, and then rotating the outer rotor will result in the next, and then rotating the inner rotor, because it's like the other side of the ratio effectively, a very slow change, and that is actually what's happening. So we are actually seeing or speed change here, and it actually tiny, you can take my word from it, you're actually seeing, so the gearing ratios are 5.75 if you are holding the ferromatic pole rotor stationary, and 6.75 if you're holding the outer rotor stationary, and you're actually seeing it there. So that's about 40,000 lumens, and that's about, I think it's like 6.3 or something. I had it written down somewhere, but it's gone. That's an outlier, so you can ignore that. That's all good results, I can say. Okay. So then, to demonstrate that the gear is actually physically working, what I did here is I rotated. So as it would in normal operation, so the blue line is when the blue line is when the outer rotor is held stationary, and I've rotated the ferromagnetic pole, so we'll say I've rotated by 6.75 degrees, and the inner rotor by 1 degree in the same direction. So what we will be looking at here is no torque change on the system. We are seeing torque change, but very small, as in it's almost being held constant. I think the ripple here is roughly around, I think it's 5%, and that's acting on the inner rotor, and then on the outer rotor it's even less. I think it's like 0.5%. So this is showing that it's effectively seeing constant torque. This would be slightly different because in an actual prototype, because it's a force of attraction rather than so this is being forced through a rotation here, whereas in reality it would be like dragging it on. So I wouldn't expect to see so much of a torque variation, but I will still have to test that to actually prove it. But it's probably best demonstrated anyway by the ratios, which are pretty much held almost constant, effectively, like over the operation that this was through. So 45 points, so that would have been 45 degrees for the what was it? I think. Yeah, so 45 degrees for the inner rotor, and then the outer rotor would have been 45 by 5.75 or 6.75 respectively for the outer or F and B. So they are held together. So this is showing that the magnetic gear is effectively working. The concept is working. So then my analysis kind of went on to, because there's a lot of parameters in a magnetic gear that we have to. Some of them seem trivial. Like we know that like increasing the air gap, because we're dealing with magnetic interaction, that the force of attraction will go down, torque will go down. But this can't be taken just for granted, so it's to be proven. Also, to establish the relationship is quite important just for future design, because the hope is that there will be an optimal design. This will be, as in, all these tests were done to kind of establish this kind of basic understanding. But yeah, so as we can see, so my graphs are shocking, so this is the air gap is increasing to a set of points, and this is then the torque. So that's the torque. So we can see that reverse exponential. But I suppose it's very keen, or it's very interesting, the initial ones here, because you have that very rapid drop off and then a sloping out, but this is, that's effectively zero. But I suppose the opposite of this then is that, air gap design, I know there are whole PhDs based in it, because ideally we want it as close as possible, but this, especially in the magnetic gear, because you have very high force attraction, so there will have to be a balance between it, because you can't have like a excessively small. So what is the air gap supposed to be? What's it varying from? So it's varying from it is 1.5 millimeters up to, I think it's like, let's say like 20 centimeters, if I can. 10 centimeters. So 1.5 millimeters up to.
That's 0.1 meter. The last one.
Yeah. Sorry. Yeah. I'm sorry about the graphs. It looks a lot clearer on the thing. So like you would never have an air gap that's 10 centimeters, but it's just to show, I suppose, where the trend is going. And this was just So what I also did, so this was purely linear, and this was rotating this was I did it on all the rotors, but this is just showing the outer rotor because it's representative of the torque across the whole system. But the important part here was that because you're dealing with the way the magnetic fields interact with each other, I wanted to make sure that increasing the air gap didn't change your points of highest and lowest torque, and it didn't. Very good. Then your ferromagnetic pole width. So this is the other thing you have quite control of. So we are limited with our. I mean, one of the main things would be your magnetic height, but we are limited to what industry standards will buy without spending lots of money designing a new one. So these, I think these were maxed with. I think it was like 2 to 4 centimeters in height, kind of quite small. But yeah, so this was increasing the ferromagnetic pole piece from 5 millimeters up to 24 centimeters. So it's huge. But you can see that initially it's a huge jump up. This was found to be pretty much due to the linear relationship between the magnetic material on the outer rotor. So of course, as you're increasing the ferromagnetic pole width, because the axial width, you're increasing the radius of the outer rotor. So you actually have more magnetic material. But interestingly, it's not linear. I mean, like it does level out, and this is because we think, I'm pretty sure, that the magnetic circuit that is required from the magnetic pole pieces becomes too big, so the magnetic field actually just loop back around. So it's then a failed magnetic gear. But I mean, we can see that there will be some optimal size here, and I think it's roughly to do with the height of the magnet, but I'm not found that yet. It could also be with the air gap, but there is definitely more testing required. But it also didn't change the points of highest as well, highest magnetic torque and the minimum, which is good. And then so one of the most useful things, which I suppose you would probably intuitively know, but it's still good to prove it. It also allowed me to do my anatomy 2D and 3D. But this is the axial length of the magnetic gear system, so you can see it's pretty much linear, and that the longer it is, I mean, you're increasing your torque. There is some this was also used to test the difference between, because all my most analysis were to do with time, so they were 2D solvers as opposed to 3-dimensional solvers. So at the start, it looks like the distance is actually increasing, but the percentage is actually massively decreasing. This is probably to do with fringing effects, because this is quite a small magnetic gear, because the big one took days to solve, but I had to cut it down. So the difference between them is actually decreasing. So I think for a larger magnetic gear, it wouldn't be a problem. I mean, you would probably have to do your 3D analysis for prototype, but for all initial design, it should be totally fine. So I thank Marcus and Richard, who is here today, and Alice McDonald from Strathclyde. Huge support and help. University of Edinburgh, of course, and I'm paid to be here by EPSR, so thank you to them as well.
This production is brought to you by the University of Edinburgh.